Hello, my dear learners. Today we will cover the topic magnetic fields in our subject antenna and wave propagation. Actually, the content which I will discuss, it is a part of electromagnetic field theory, and in my last lectures I have discussed briefly about the electrostatic field. Now it's turn to discuss about magnetic fields. There are large number of content given in the different books, in the different videos, but I will discuss only those important aspects of this particular topic which are important and associated with the electromagnetic field theory as well as antenna and wave propagation. So, let us start about the magnetic fields. The introductory part of this topic magnetic field is based on some of the relevant parameters in which we can compile the theory of magnetic field with the previously defined electrostatic field. We have already studied about the charge density and we know the basic source of the charges, what is the charge density and in which form this charge density can exist. Now, the heading of this slide as continuity equation. Before starting magnetic field, it is essential to know about the continuity equation. What is this continuity equation and what it provides in the topic of magnetic field? Actually, continuity equation is the equation which correlates the charge density with the current density. In the larger or broader side of the subject antenna and wave propagation, when we define the radiation from an antenna, then radiation means electromagnetic waves, the generation, the production of electromagnetic waves from a linear conductor, that is antenna. It means the antenna is capable to produce the electric field and magnetic field both simultaneously, and this is the theory where we use the charge density and current density both as the sources of electric field and magnetic field in any conductor or any antenna. So, I am trying to relate this continuity equation with the electromagnetic field theory as well as antenna and wave propagation. So, let us start the topic continuity equation. So, by using the different mathematical notations in the continuity equation, we have to discuss what is the charge conservation and how this charge conservation and its mathematical analysis is directly related to the continuity equation. How we can get the continuity equation by using the conservation of charge. According to the principle of this charge conservation, the time rate of decrease of charge within a given volume must be equal to the net outward current flow through the closed surface of the volume, and it can be written like this. What is given here? It is given I out, outward current, that is equal to closed integral of J dot ds, current density dot differential surface area, and it is equal to minus dq in upon dt. What it denotes? It denotes here the negative sign denotes the decrease of charge, where this q in is the total charge enclosed by the closed surface. Here we can use the divergence theorem. When we use the divergence theorem in terms of J dot ds, and this integral becomes the volume integral of del dot J dV. Means by using the divergence theorem we can convert the surface integral into volume integral, and when we get this particular parameter in this form, we can also write minus d q in by dt is equal to d by dt, where q in is the total charge. So, we can also write this in the form of volume integral as volume integral of rho v dv, which is equal to minus volume integral del rho v upon del t and its integration with respect to its differential volume dv. What is the next? Now, this complete by using the divergence theorem and its different aspects, we define this like volume integral del dot j dv is equal to minus volume integral del rho v upon del t dv, or the interior part of these two volume integrals must be equal to each other, and we can also write that del dot j is equal to minus del rho v by del t. What it says? Actually, this is the equation which is known as the continuity of current equation, and this continuity of current equation describes the relationship between the current density and charge density. How the charge density is related to the current density? It means the divergence of current density is equal to the decrease of volume charge density with respect to time. This is all about the continuity equation. There is another very important parameter which is known as the relaxation time. The relaxation time also comes out from the continuity equation, and by using these two different laws, we can identify the relaxation time. How? As we know, according to the Ohm's law, this J is equal to sigma E. What is this? Means current density is equal to sigma E. Sigma is the conductivity and E is the electric field intensity. At the same time, we can also describe the Gauss's law as del dot E is equal to rho v upon epsilon. What it says? It says that divergence of electric field intensity is defined as the volume charge density upon epsilon, and this epsilon is the permittivity of the medium. So, conductivity and permittivity of the medium are related to each other by these two laws. We can describe it very briefly. Now, in the continuity equation, we can put these values, and by using these both laws in the continuity equation, we can also write that del dot sigma E, where del dot j was written, here we can replace the j as sigma E. Del dot sigma E is equal to sigma rho v upon epsilon, that is equal to minus del rho v upon del t, or we can also write that del rho v upon del t plus sigma upon epsilon rho v is equal to 0. Directly we can write it, and when we write this kind of equation, this is a homogeneous linear ordinary differential equation, and by using the separation of the variables, we can get the equation like del rho v upon rho v is equal to minus sigma upon epsilon del t. Now, we can integrate both the sides, and when we integrate both the sides, we get the equation like ln rho v is equal to minus sigma t upon epsilon plus ln rho v naught, where this ln rho v naught is a constant of this integration, and it defines that the equation of the volume charge density becomes in the form of rho v is equal to rho v naught e to the power minus t upon T r. What is this T r? Tr is equal to epsilon upon sigma. It means this rho V naught is the initial charge density, where that ln rho V naught was the constant of integration, but individually this rho V naught is the initial charge density, or we can say the volume charge density at the time instant t is equal to 0. All the discussion which we considered, the summary, the result can be written in this form. Above equation shows that as a result of introducing charge at some interior point of the material, there is a decay of the volume charge density rho v. This is a 100% fact that the time constant Tr is known as the relaxation time, which is defined in an individual way, because it plays a very important role to define the description and the mathematical analysis of the magnetic field. Further, relaxation time is the time in which a charge placed in the interior of a material to drop to e to the power minus 1 means 36.8% of its initial value. This is the physical significance of the relaxation time Tr. If charges are moving with constant velocity, a static magnetic or magnetostatic field is produced. Thus, magnetostatic fields originate from currents, for instance, direct currents in current carrying wires. This is the basic theory of magnetic field, which says that how these magnetic fields are generated. Most of the equations we have derived for the electric fields may be readily used to obtain corresponding equations for magnetic fields if the equivalent analogous quantities are substituted. Further, when we discuss the different parts of magnetic field, we see that a large number of equations which we already used in the electrostatic field will be given in a different manner. Okay. So, next come to the point electromagnetic force. What is electromagnetic force? अगर आप मेरे शुरू से लेकर के अभी तक के सारे लेक्चर्स देखेंगे तो देयर इज अ कंटिन्यूटी. I am not directly talking about the magnetic field. It is a link between the electric field and magnetic field. What is the relation between the electric field and magnetic field? And when this link has been established, then I will talk about the electromagnetic force. The electromagnetic force is given by Lorentz force equation. Lorentz was a scientist, and this name was after a Dutch physicist Hendrik Antoon Lorentz, and he has given an equation in the form of F is equal to Q into E plus U cross B. What this equation says? This equation says that F means that electromagnetic force. Electromagnetic force means electric force, magnetic force, both are working on a conducting element, and when these both forces are acting, then this force can be calculated like F is equal to Q in bracket E plus U cross B, where Q is the charge, E is the electric field intensity, U is the velocity of the charge, and B is the magnetic flux density. So, simply the Lorentz force equation is quite useful in determining the paths which the charged particles will take as they move through electric and magnetic fields. If we also know the particle's mass m, the force is related to the acceleration by the equation like F is equal to m into A. This is the force which is exerted by a particle of having a mass of m and which is moving with an acceleration of a. The first term in the Lorentz force equation represents the electric force F e. F e means the force which is exerted by the electric field and which is acting on a charge q within an electric field, which is given by F e is equal to q into E. Q is the charge and E is the electric field intensity. It means any charged particle which is moving under the influence of an electric field E will experience a force of F e, and the electric force is in the direction of the electric field. Now, next, what is magnetic force? The second term in the Lorentz force. What it says? It says the equation represents magnetic force F m in Newton on a moving charge q in Coulomb is given by F m is equal to q into u cross b, where the velocity of the charge is u in meter per second within a field of magnetic flux density B, which is measured in Webers per meter square. The magnetic flux is measured in Webers, and when we talk about the magnetic flux density, it is measured in Webers per meter square, and the units are confirmed by using the different equivalences. You can note down, you can see, and by using the different equations and formulations we can derive. The magnetic force is at right angles to the magnetic field. These are very important points which you have always keep in your mind. The magnetic force requires that the charged particles be in motion. It should be noted that since the magnetic force acts in a direction normal to the particle velocity, the acceleration is normal to the velocity and the magnitude of the velocity vector is unaffected. Here the cross product of u cross b, it means the resultant will be in the perpendicular direction to the velocity as well as the magnetic flux density. Since the magnetic force is at right angles to the magnetic field, the work done by the magnetic field is given by W is equal to integral f dot dl, which is equal to 0, because the angle between these two vectors is equal to 90 degrees. So, the cos 90 is 0. So, the complete work done is equal to 0. This is a very important law in the magnetic field. Actually, this is a very similar law as we have studied in the electrostatic field, likewise Coulomb's law. In the same manner, after the Oersted's discovery, what was that discovery? That discovery was the currents produce magnetic fields. This was a discovery by the Oersted. After this discovery, Jean-Baptiste Biot, this was the name of the scientist, who has been known for his invention for getting the magnetic field, and the magnetic field intensity dH produced at a point P by the different current elements IDL is proportional to the product of IDL and the sine of the angle between the element and the line joining P to the element, and it is inversely proportional to the square of the distance r between P and that current element IDL. This is very similar to the Coulomb's law, and from this figure you can also see that the magnetic field, which is denoted here by dH. Biot-Savart's law can be represented in its mathematical formulations like dH2 is equal to I1 dL1 cross A12 upon 4 pi R12 square. It means this is the magnetic field produced by that ideal current element, and this A12 is the unit vector. To get the total field resulting from a current, you can sum the contributions from each segment by integrating. So, the integration is taken here, and the Biot-Savart law is analogous to the Coulomb's law equation for the electric field resulting from a differential charge element. You have already studied about it. This is the theory of electric current, because as the charge is moving, the current is produced, and this is given in the form of I is equal to dq upon dt, and the SI unit of the current is ampere. 1 ampere is the flow of 1 coulomb of charge per second. This is the current density, the magnitude of current density J, it is equal to the current per unit area through any element of cross section. It has the same direction as the current, which is given as I is equal to integration of J dot dA. If the current is uniform across the surface and parallel to dA, then this J is also uniform and parallel to dA, and then it can be given in the form of this equation, where A is the total area of that surface, and the SI unit, the current density, is represented in form of ampere per square meter. The form of different current densities are given in 3 terms like line current density, surface current density, and volume current density. All these 3 factors are similar as the charge densities. You have already studied about this, where this line current density, surface current density, and volume current density are being used. This is the electric current in a conductor, where the current density is defined in terms of sigma E. We have already used in the continuity equation, and this is very important, Ohm's law. This current density is equal to sigma E, where sigma is the constant of proportionality, which is known as the conductivity of the conductor. Some of the important aspects of surface current density and volume current density are described here in these 2 slides, because it is very essential to know how these surface current density and volume current density are being used, because in the theory of antenna we will use different kinds of antenna. They may be linear, they may be bulky, they may be in the form of a surface, they may be in a form of container. So, the different kind of current densities are also considered for the further studies. Here you can see how this surface current density and volume current densities are defined. So, in my lecture I have covered the basic concepts of the magnetic field, what are the prerequisites to know, to study about the magnetic field. I hope you will understand and you will get the different aspects of this magnetic field. So, I request you to go through all these slides very carefully, because in my next slides the electromagnetic field and the complete wide variety of the field which exists in free space will be dealt in another form, because antenna and wave propagation is the subject for which these electrostatic field and magnetic field both are very important and very relevant prerequisites. So, I hope you will understand the concepts which I have discussed in my this lecture. So, thank you very much for watching this.